In this lesson, we'll learn about solid materials, Hooke's law, the limit of proportionality, the elastic limit, spring constant, elastic strain energy, forced extension graph, stress, strain, Young's modulus, and stress strain graphs. We'll learn about some other stuff that we haven't mentioned here before. So, starting from Hooke's law is basically a statement which says that the force needed to extend a spring is proportional to its extension. So if I have a spring over here, doesn't have to be a spring, it can be any material. So if I hang some mass on it, the force on the string would be the weight of those mass. This is the force on the string. When we hang something on a spring, the spring will get longer than it was. So this is what it would be. So this was before the weight was added and this is after the weight was added. So this is the extension. We write extension as del x. This sign represents change and this is the length. X is the length of the string and this sign represents change. So extension is the change in the length of string. The force on it is the weight of the mass we have hanged over here. This Hooke's law states that this force should be proportional to the extension. So F will be equal to K del X. This constant over here is the limit of proportion. This constant over here is the spring constant. This is also called the stiffness constant. Now we want to find the unit for it. If I make K the subject, I'll get force divided by extension. The SI unit of force is newtons, the SI unit of length is meter. So the unit of K is Newton per meter. Usually for different materials, it obeys the Hooke's law up to a certain mark, and after that it starts to flatten out. So up to this point, the straight line part, this part over here is the straight line. After that it curves. So the point at which it starts curving, so this point is called the limit of proportionality. So up to which point the curve is proportional. So up to the point where force is proportional to extension, this is limit of proportionality. So if I want to define the three terms we have learned so far, so Hooke's law, stiffness or spring constant, and limit of proportionality. So this is how we define them. We can also say that the stiffness constant is how stiff an object is. If the stiffness constant was greater, it would mean that it's more stiff. So basically I have to apply more force to cause the same extension. So for the same extension, in this case I have to apply more force than for this. So I have to apply more force here. Now going back to the graph, we have to learn about the elastic limit. So if I usually have a spring that's loaded with a small mass, if I remove the mass, so if I remove this, it will go back to its original shape. However, if I put a very large mass on it, so very heavy mass, it will extend a lot. So the spring will become something like this. And if I extend it too much, after I remove the mass, it will not go back to its original length. It will become bigger than it used to be. So it was this size when it started, but after deforming means changing the shape, and removing the mass, it does not return to its original shape. If it returns to its original shape, we say that this is elastic deformation. So even in this case, the size and shape of the spring changed. So it was this one before, and now it's a bit larger. This is called elastic deformation, because if I remove this mass, it will return to its original shape. However, in this case, we call this plastic deformation, since it does not return to its original shape. If I want to represent this in a graph, I'll draw a force extension graph. This is the force, this is the extension for a spring. After this, it will become something like this. So this is the limit of proportionality. A little bit after that, we'll have the elastic limit somewhere over here. This is the elastic limit. This is the most force that, so if I remove the force from the elastic limit, it will return to its original shape. However, if I cross the elastic limit and go up to here and then remove the mass, the unloading curve, so the force extension graph when we are removing the mass would look like this. This is the unloading graph. And the white one is the loading curve. This is the amount that we have plastically deformed our spring by. So if it was, so if this value is 1, our spring will now be 1 meter more than it used to be, or whatever unit. So if I have centimeters over here, the spring is now 1 centimeter larger than it used to be. The area closed off by this, so this area over here is the work done to cause the plastic deformation. And if I want to define the elastic limit, I have to define it in terms of the extension over here, since that is on the x-axis or the independent variable. If you think about it practically, the force should be the independent variable, since we are in control of the masses we are adding, but not in control of how much the spring will change its length. But for this case, we draw force extension graph instead of extension force graph, because from here we directly get the spring constant. And we define all of the limits here using the extension. So even if you look at the limit of proportionality, it was the maximum extension that an object can have, not the force. So similarly for elastic limit, we define it in terms of the extension. So this is how we define the elastic limit. We define it as the maximum extension that a material can undergo and still return to its original size after the force is removed. Now, similar to extension, we can have the same case for compression. So instead of a spring being hung from the ceiling, we can have a spring that's set on the floor, and then we can add a mass on it. So we can have a spring like this and then add a mass on top of it. So now instead of extension, the spring will be compressed. So I have a mass on top of it. The change in the spring's length is the compression right now. This del x was the extension. It was how much the spring got bigger. This over here is compression, by how much the spring shrinks. This would be similar to it. So the del x would, instead of being extension, would represent compression. The definition will also remain the same, just instead of extension we'll write compression. So instead of extension over here we'll write compression. Here instead of extend we'll write compress, and this will be compression, and this will again be compression. Now we'll learn about elastic strain energy. Elastic strain energy is basically the energy or the work done when we extend a spring. So when we are extending a spring, we are applying a force which causes the spring to deform or which causes the mass to move. The force is in the direction of the displacement. Here del x is the displacement. So work is done as work is force into distance. In this case, the elastic strain energy will be the area under the graph. And if we don't cross the elastic limit, this work will be stored as the elastic strain energy. The work done is the area under this graph, and if we don't cross the elastic limit, this will be this area over here will be the elastic strain energy that is stored. However, if we cross the elastic limit, so if I go up to here, the stored energy, this blue area will be lost since we are using that to deform the spring. The remaining part will be the elastic strain energy that we store. This is how we define elastic strain energy. So the work done in deforming a material sample before the elastic limit is stored within the material. This is the elastic strain energy. Now, since the area under the graph, there will be a triangle. So as it obeys Hooke's law over here, this area will be a triangle. This is F, this is del x. So the energy, elastic strain energy or energy elastic, is equal to half into F into del x. Sometimes we might also have to use the equation F equals to K del x. If we put the value of F over here, so instead of F I write K del x, I'll have half K times del x, so half K del x square. K is a constant, so the energy or the elastic energy is proportional to the extension squared. We might have to use that fact in some cases. In some cases, we are given to find an estimate of this area trapped between them. So we might be asked to find this area. So this one is the loading curve and this one is the unloading curve. We have to find the area between them. This isn't a general shape that we know the area of. We have to use an estimate over here. So to estimate this, I'll have to first find how much one box represents. So this is one box. How much does this represent? How much energy does this represent? Since this is the area of a force extension graph, the area will be the energy. So this over here is 1 Newton and this over here is 1 meter. So the energy of each box is 1 into 1, so 1 joule. So each box is equal to 1 joules. Now I have to find an estimate for the number of boxes. First, I'll see how many boxes that are covered fully. So the boxes in between that are fully inside this region. So if I start counting them, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I have the slightest doubt that it's not fully inside, I'll not take it. So in case of this box, just this part was missing, but I'll still not take it. Over here as well, only this part was missing, but I'll still not take it. Here as well, I could take this one. Yeah, I could take this one. This is almost fully covered, and so can I can take this one as well. So in total I have 14 full boxes. Now I have to find how many boxes are partially filled. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. When I count partial boxes, no matter how small it covers, I'll still take it. So this is 9, 10, this small part is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 and 29. I have here 30. Did I miss any one of them? I don't think so. There will be some margin of error when we do this. So the energy or work, this part over here can also be lost as heat energy. That happens in case of rubber bands and we call it hysteresis. Hysteresis simply means that the loading curve and unloading curve is not the same. So W, or the area in between them, will be the number of full boxes, which is 14. So we have 14 full boxes plus the number of partial boxes divided by 2. We have counted 30 partial boxes, so 30 divided by 2, and we multiply this whole thing with the area of each box. So this is 1 joule. So the work done will be 14 plus 30 by 2, which is 15. So 29 joules. Up next we'll run about stress and strain. Stress is related to force and strain is related to the extension. We want to find stress and strain because force and extension depends on the area and the length of the spring or wear we use. However, in case of stress and strain is fixed dependent on the material we use. So for steel, if I make springs of different length and different area, the stress and strain will still remain the same, although the force and extension might. Stress is defined as force per unit per area. So if I have a wear, its stress is also written with the Greek letter sigma. This will be force per unit area. So force is the force we apply on this wear and the area is the cross sectional area. So if I cut the wear through its length, we'll get something like this. This is what we'll see if I cut the wear along its length. This is the area I want to find. And strain, we can also denote it with this Greek letter. Strain is the extension per length of wear. So if I have a wear and then apply some force on it or stress on it, it will extend a bit. So this might be the extension. The strain is the extension divided by the original length. X is the original length of the wear before anything was added to it. If I look at the units of force is Newton and the area of and the unit of area is meter square. So this is Newton per meter square. This can also be written as pascals. So the unit of stress is Pascal. Now if I look at strain, the unit of extension is meter, the unit of length is also meter, so they cancel out. Hence, strain has no units. Now if I look at the differences between force extension and stress strain, so this is the difference between them. Force extension depends on the dimensions while stress strain only depends on the material. Force extension depends on both dimensions and the material, not only the dimension. Now, Young's modulus is basically the equivalent of the stiffness constant but for stress and strain. So the stiffness constant here was force divided by extension. Now in this case, Young's modulus, which we denote with a capital E, can be written as stress divided by strain. So we have a unit of Pascal on the top and no units on the bottom, so the unit of Young's modulus will also be Pascals. Young's modulus also only depends on the material. So for the same material, the Young's modulus is a constant. So for all types of steel in any shape, the Young's modulus will be the same. However, the stiffness constant will depend on the shape of the sample we are using. For both cases, we have to maintain that Hooke's law is obeyed. So if I go beyond the elastic limit, beyond the limit of proportionality, this equation and this equation will not work. So both of them have to, for us to use any of them, we have to be under the limit of proportionality. Likewise, before we were drawing force extension graphs, now we can draw stress strain graphs. So on the y-axis we have the stress in pascals, in the x-axis we have the strain which has no units. The general stress strain graph we get will be beginning as a straight line and then start to change like this. This is just as before, but now after this point it will go down and then follow a shape like this. Up to this part around here we had elastic deformation, so everything on the left is called the elastic region and on the right we call that plastic region. On the right we have the plastic region where the deformation is permanent. In elastic deformation, if I remove the force, we'll just get our object back in its original dimensions. If we have plastic deformation, however, this will not happen. So we have to remember some key points over here. So this is the point of limit of proportionality. This point over here is the elastic limit. This point over here is the yield point. Now we have learnt about the other 2 points before, but we haven't learned the yield point. So what is the yield? After the yield point, the atom or whatever we are using, the sample's atomic structure changes. This causes it to suddenly have a large change in the strain. So suddenly it has a large extension since the atomic structure is now being changed. The next point is the highest point of this graph. This is called the ultimate tensile stress, or this is the maximum stress that the material can withstand. This is written UTS in a short form. This is the highest stress this material can. One difference over here, in the force extension graph, we were defining the points with the x values, but over here we are defining the values in terms of stress, which is in the y axis. This is a slight difference between the stress strain and force extension graph. And the final point is the breaking stress or the fracture stress. It is defined as the value of stress when the material breaks. So this is how we define the fracture stress. Now we'll learn some different types of materials and their corresponding stress strain graphs. Okay, before we go on to that, we'll go on our stress strain graph. Now the gradient of a stress strain graph is the Young's modulus, just like the force extension graph having a gradient of k. The area under a stress strain graph will be half into force by area into extension by length. So we'll have half, if I write half into f del x on top, I'll have a times x on the bottom. The area times the length will be the volume. And if we look at the top, this is the same expression we had when we are finding energy. So that will be the energy or elastic strain energy. So this is the elastic strain energy per unit volume. This is also known as the energy density. This doesn't come in the exam as often, but this might come as a suggest question. The properties we'll learn are hardness, stiffness, which we already have gone through. So the remaining are the hardness, the toughness, the brittleness, strength, malleability, and ductility. This is the hardness is a property which makes it difficult to scratch. So if I take a knife and a paper, if I move a knife across a paper, the paper will be scratched, not the knife. So to find which is the tougher or which is the harder of the two materials we want to find, we'll just scratch them against each other. The one that gets scratched is less hard than the other one. Now the next property we'll learn is the toughness. The toughness basically means how much energy that a solid can absorb without breaking. And to do that, they must undergo a lot of plastic deformation. So if I can deform them, it means that it's absorbing a lot of the energy. So if an object is tougher, the area under the stress strain graph will be greater. So for the object which has the greatest area under the stress strain graph, that will be the tougher object. The next property we'll learn is brittleness. Brittleness is how easily an object breaks. For example, uncooked spaghetti is very brittle. If you apply a little force to it, it will instantly shatter or break. Glass is also a brittle object. Brittle objects do not undergo elastic deformation, plastic deformation. So if you apply slight plastic deformation, it will shatter. So for tough materials, for brittle, so this will just extend up to the point it's elastic, and at that point this will break. It will not go through plastic deformation. So a brittle object is an object that shatters very easily, and a property of that is that they undergo very little or almost no plastic deformation. Now the next property is the strength. The strength depends on how much stress an object can withstand at max. So basically, if you have a higher UTS or ultimate tensile stress, that means the material is stronger. So a stronger material has a higher UTS. That's it. So this is how we define it. The next two properties are closely linked to each other. One is malleability and one is ductility. Malleable means that it's good under compressive stress. So it can be beat down into stuff. Gold is a malleable object. If I hammer gold, it will turn into a flat plate over here. So I can take a gold sphere and then hammer it down into a sheet of gold, even without it breaking or fracturing. We are saying compressive stress because when we hit the gold, it's forced inwards, so there is a compressive force on it or a compressive strain on it. And ductility is the opposite. Ductility is the ability to be drawn into wear. So if I have a copper sphere, I can pull it apart and then form a copper wire with it. So that is ductility. Just the opposite of malleability. Ductile materials are good at absorbing tensile stress. Malleable objects are good at absorbing compressive stress. ductile objects are good at absorbing tensile stress. Tensile stress is the name when we are trying to pull apart something or extend something. Compressive stress is when we're trying to push something down or compress it. So now if I have the stress strain graphs for three objects, I can find which one has which property. The gradient means the stiffness. In this case, the Young's modulus. The greater the Young's modulus, the more stiff an object is. So this is one material. We have another material over here and another over here. This material, so I'll name them 1, 2 and 3. The area under the graph for object 2 is the greatest, so it's the toughest object over here. So this is the toughest. Object 1 has the highest gradient, so this is the stiffest. It also has the highest UTS value, the highest. Since it has the highest UTS, it's the strongest. And it doesn't show any plastic deformation. It just after reaching the elastic limit, it breaks down, so this is brittle. Object 2 shows a lot of plastic deformation, so this is not brittle. And object 3 has a very small gradient, so this is the least stiff. And if I want to find how ductile a material is, we'll look at how much plastic deformation it can show. If we look at this, copper is, so the third graph, this is for copper, is showing the most plastic deformation. So this must be the most ductile, as it has the longest plastic region or largest plastic region. So this graph was for high steel, mid steel and copper. That is high carbon steel. So this steel has a very high carbon concentration, while this has a milder concentration of carbon, so that's why the difference in name. And we don't have to worry about the objects, we have to worry about the properties of them. So number 1 or high steel is stiff, strong and brittle. Number 2 is tough, while copper is the least stiff and the most ductile over here. And that's it for solid materials.